Okay, we continue our discussion of vectors now in n space, and we want to define a couple things here. You can see the norm, the dot product, and distance in n space. So what are these things? So first of all, the norm, essentially it's the equivalent what we think about as the length or magnitude of a vector. So in 2 space, right, we can represent a vector geometrically. Its initial point is at the origin. Let's suppose this vector, let's just give this vector a name, a comma b, all right, which means that in 2 space we can think of the a as being sort of the x component, if you will, and b being the y component. And again, this is a 90-degree angle. So the length, geometrically, the length of this line segment would be the magnitude of the vector, or the length. And we're going to denote that with this symbol here. Notice it's sort of double lines, like almost like double absolute value. It's not absolute value, but this is the notation for the length or magnitude, or what we will call in a minute the norm of a vector. Some books will use just a single vertical line for the norm. But we're going to use the double line notation to be consistent with this current textbook. So there is the norm. It's this length, right? It's this length. And so we can see the relationship between the norm, which is a length, which is a real number, right, a magnitude, and the real numbers a and b by the Pythagorean theorem, right? The Pythagorean theorem tells us that the magnitude of or the magnitude squared, right, this length here, which is also called the hypotenuse in this right triangle, is equal to the sum of the squares of the remaining 2 sides. And so I can solve for the norm, well, the magnitude, which we'll call the norm in a minute, by taking the square root. Okay, so algebraically, this is now how we can express the length or magnitude of a vector in 2 space, and we extend that definition then very easily then for a vector in n space, right? Then the norm of this vector, which is also called the length or magnitude, but norm is what we're going to use now, denoted the same way, right, is given by this. It's just the square root of the sum of the squares of the components. Okay, so that is the definition of the norm, and it's a measure of the length or magnitude again of this vector. This is also, we will see the Euclidean length or norm, and we'll talk more about non-Euclidean norms and later when we get into inner product spaces. So some properties of the norm: if v is a vector in n space and k is any scalar, the norm is always non-negative, greater than or equal to 0. And the norm is equal to 0 if and only if the vector v itself is the 0 vector. And then 3, any scalar multiple of v, its norm, is the absolute value of that scalar times the norm of the vector. It's real important from the first one. The norm is always greater than or equal to 0, and so we've got to make sure that it's the absolute value there for sure for that to work. Let's actually prove why this is true, and we'll do number 3 here. When I take a look at this expression, right, we can think of v, if we think of v as having the same n components, then this is the norm of k v1, k v2, all the way to k vn. Okay, and by definition of the norm, all right, it's just the sum of the squares of its components. In this case, the components are k v1, square that, k v2, square that, and k vn, square that, sum of the squares of all those. Okay, so again, this is a scalar quantity now, and because these are scalars, I can indeed in each case, a product to a power, I can distribute that power, right? The product to power rule for exponents, 2 squared, and then this will be k squared vn squared. Okay, and then notice there's a k squared factor common to all of these. I can factor that out, and I'm left with v1 squared plus v2 squared all the way to Vn squared. Now, this is the little trick here. Obviously, when I have a product of two things, the square root of the product of the two things, that indeed is the product of the square roots. Again, it's really the product to power rule, because the square root is to the 1/2 power, right? So I can distribute that to both of these. Okay. Now, here's the trick, right? Clearly, this is the definition of the norm of the vector v, right? That's the definition of the norm of the vector v. So this indeed is the norm of the vector v. But here's where a lot of you forget that if I square k and then take the square root, what do I get? The answer is not k. In other words, if I write this statement here, the square root of k squared equals k, this statement is false. It is not true. And I'll give you an example, right? Let k be -1. If k is -1, on the right side we have, of course, -1. Over here, if I square -1, I get +1, and the square root of +1 is +1. 1 does not equal -1. Any negative number will make this statement false. So in fact, this statement is true for all positive real numbers, but in general it's not true. What makes the statement true? That, right? That's actually the definition of the square root of k squared. And that's essentially right there, the why we have the square root of k in the proof. And of course that proves what we were trying to do. So be real careful. This is often a missing point when I ask find all the values of k such that the norm of kv is equal to some number. You forget that we have to look at that as being the absolute value of k there. And basically the idea is, if I have k times v, if k is positive or negative, what's that doing? It's just changing the direction. The length is still the same. So there's actually two k values we can have where the norm is equal to a fixed number. So there'll be some homework problems where you will look at that. Continuing on, now that we have norm, we can talk about unit vectors. Unit vectors are vectors that have a norm of 1. So their length or magnitude is 1. Thus, v is a unit vector if and only if the norm is equal to 1. Now in 3 space, some of you are familiar with I, j, and k. These are the vectors in 3 space that a lot of you are familiar with. They point in the positive x, y, and z direction. And you can see clearly that their norm is 1, their length is 1. Now in n space, we have the extension of these unit vectors. The standard unit vectors, or sometimes called the standard basis, we'll see later in n space, are these n vectors. And you notice the first one has a 1 in the first component and zeros everywhere else, and then a 1 in the second component, zeros everywhere else, and so on until we get to the last one with a 1 in the nth position. Every vector in n space can be written as a linear combination of these standard unit vectors. So if I have a vector, right, that is an n tuple that resides in n space, then I can write out this linear combination quite easily, right? Quite easily. And you guys are familiar with this, right? If I have the vector 3, 2, 1, that would be what? 3i plus 2j plus 1k, and that's the same idea here. One neat little thing is to find a unit vector in the direction of a given vector. This vector resides in 4 space, so let's do that here. Sometimes this is known as normalizing the vector. And the idea is, if I have a vector, and I'll pretend it's a vector in the plane pointing in some direction, say this is the tip and the pen, this is the initial point rather, and the terminal point, right, where the pen tip is. So, the length of this may not be 1, but to get a unit vector in that same direction, right, I want to scale it down so the length of the vector is 1, but it points in the same direction. So I just need to scalar multiply essentially by the reciprocal of the norm, right, reciprocal of the norm. Well, let's see first of all if we even have to do this, because if I take the norm of the vector u and it's a unit vector, then there's nothing to do. It's already a unit vector. But that's not going to be the case here. When I find the norm of this vector, we get the square root of 4, negative 1 squared is 1, 0 squared is 0, negative 2 squared is 4. I get 4 plus 1 plus 4 is 9, square root of 9 is 3. So obviously my vector is not a unit vector, it has a norm or length of 3, and so to find a unit vector in the direction of u, I'm going to scalar multiply by the reciprocal. Okay, by the reciprocal of the norm. So that's going to give me a unit vector. Someone says, well, why don't we just divide by the norm? You can't divide a vector. We can scalar multiply, we can't divide. So only scalar multiplication. So essentially you're thinking of this, right? And so what is this? This is going to be 1/3 times the vector 2, negative 1, 0, negative 2. And we get 2/3, negative 1/3, 0, comma, negative 2/3. And you can check and confirm, take the norm of this vector, and it will be 1. And that's important to realize there. Okay, so we've talked about the norm and unit vectors. I now want to talk about distance between vectors. So how do we define distance between vectors? So here is how we do that. If u and v are vectors in n space or points, and remember that's real important because they're essentially the same thing. Taking the terminal points of the vectors are really essentially the same as the vectors, since our initial point will always be at the origin. Then the distance between the two vectors, which is denoted this way, is defined this way. It's the norm of u minus v, which then would be defined this way. Well, let's see why that is in 2 space. So if I have the vector u, maybe looks like that from the origin, and then we'll do vector v from the origin too. Maybe it looks like this. Okay. So what's the distance? Well, really what we're saying is the points, right, the terminal point of u and the terminal point of v, this is the distance we're looking for. This is the length of really the line segment connecting these 2 points is what we're talking about. So why is it the norm of u minus v? What would u minus v look like, by the way? Well, if this is u and this is v, what would minus v look like? It would have this same length, but what, point in the opposite direction. So what I'm going to do, I'm going to do, right, u minus v is the same as u plus a negative v, right, is really what we mean there. So I'm going to take positive v, and I'm going to, form negative v, which will be in the opposite direction, and add that to u. So I would get, going in this direction, right? This is the vector negative v, right? And then how do we add u plus negative v then geometrically? It's going to be that vector, u plus a negative v, which is u minus v. Well, that's the vector we're saying take the norm of that vector to find the distance between the points u and v, which is this distance here. Well, do you see this vector here, right, is the same as the vector from the tip of v to the tip of u. In fact, that's an interesting way to think about it, but that's how you would draw u minus v. You would draw u and v extending from the same initial point, and to draw u minus v, you would actually go from the tip of v to the tip of u, and we get the length of that. The norm of that, or length of that, obviously is the distance between those 2 vectors, or the distance between their terminal points. Now, here's the thing. I went through all that discussion about the right direction. Does it matter if I get the direction correct? What if I did, instead of u minus v, what if I did v minus u? Well, that's going to be this same length, but just going in the opposite direction. So it actually doesn't matter. This is also the same as the magnitude of v minus u. So you really don't, and if you get the which order, is it u minus v or v minus u? It doesn't really matter. Okay, you'll take the norm of either vector will give you the same number. That is the distance between those points. Okay. We're now ready to, we've talked about the norm and we talked about the distance between points. Now we're going to talk about something known as the dot product. Some of you are familiar with that, and I've already mentioned the dot product already, but we want to develop this a little bit. First of all, we start in 2 and 3 space. We can define the angle theta between the two vectors, and by that, when we say the angle between the two vectors, we mean the smallest angle between these vectors. So for instance, if these are two vectors, this is the angle between the two vectors. Here, this is the angle. Okay. Now there's another angle between these two vectors. I mean, I can go all the way around here, right? Have this vector, but it's obviously bigger than this vector. Here, all right, the vector is, of course, obviously pi units or 180 degrees, but in radians, pi units. Here, it's not going to be this angle here because it's bigger than this angle here. This would be the angle. Okay. You can even have a situation where I have one vector, let's say pointing in this direction, and then I have another vector, same initial point, and pointing in the same direction, maybe not as long. What's the angle between these ones? The angle here would be 0. Right, 0 radians or 0 degrees. So it's always the smallest angle. So it's always between 0 and pi inclusive. Okay. Now, we're ready to now define the dot product, or what we call the Euclidean inner product. For u and v, two non-zero vectors in 2 or 3 space, and theta being the angle between them, then we define this dot product or Euclidean inner product this way: u dot v, and it's defined this way. So this is not multiplying the vectors u and v. Okay. In fact, from now on, when you're in this section, a dot cannot be used to represent multiplication anymore. Cannot be used to represent multiplication anymore. So I can only do a dot between what? Vectors. Only a dot between vectors. And notice what I get when I take the dot product, we say, of these two vectors u and v. The magnitude of u, which is a scalar, times the magnitude of v, which is a scalar, times the cosine of the angle between them, which is a scalar. This is a scalar. This takes two vectors and outputs a scalar. Because of that, it's sometimes called a scalar product. Okay. Now, if you're interested, in finding the angle between the vectors, I can solve for cosine theta by dividing by the norms, right, of the product of the norms here on both sides. And again, assuming that they're both non-zero, we can do that. And then once you have cosine of theta, this number here, you can find the inverse cosine of this quantity to get back to that original angle, right, to help you find that original angle. Keeping in mind it has to be an angle between 0 and pi over 2. Now, notice if the dot product is positive, right, then this whole quantity is a positive quantity because norms are always non-negative. So if the dot product is positive, cosine of theta is positive, what do we know? The value of theta is what? In that first quadrant between 0 and pi over 2, right? In that case, theta must be acute. So in this case, right, we would get a dot product, right, between these two vectors that is positive. On the other hand, if the product is negative, u dot v is negative, then this whole thing is negative, and cosine is negative in what? Quadrant 2 between pi over 2 and pi, meaning theta is obtuse. So if the dot product is positive, we have, right, the acute angle between the two vectors. If dot product is negative, then we have an obtuse angle between the two, like this. Now, what happens if the angle between the two is pi over 2, right? Which means we would say, you could talk about maybe being perpendicular. Vectors u and v. We'll actually give that a special name later, very shortly, called orthogonal. When vectors are perpendicular, we say they're orthogonal to one another. Right? What do we know? That angle is pi over 2. Cosine of pi over 2 is what? 0. And so the dot product is 0. So that's going to be an important observation. When the dot product is 0, the two vectors are going to be perpendicular. Okay, with that, let's just talk about expressions again. When we have this dot, as I said, it cannot mean multiplication anymore. So do we have a vector, scalar, or nonsense? Well, this first example doesn't have a dot in it, but scalar multiple of a vector is a vector for both of these, and adding two vectors together is a vector. So this would be a vector. Again, we're assuming all the vectors are in n space. Here I have a dot, okay, so that's dot product. Scalar multiple of u is a vector, scalar multiple of 2 is a vector. Vector dot vector is what? Scalar, right? We said this is a scalar product. It takes two vectors and outputs a scalar quantity. U dot v, okay, that's a scalar, we just said. W is a vector. Can you add a real number to a vector? No. You can't add a scalar to a vector. So this is nonsense. Makes no sense. You can't just, that's undefined. Here I've got u dot, right? So I'm taking the dot product v plus w. Well, I can add vectors together, and what do I get? A vector, right? So this is a vector, this is a vector. Dot product of two vectors is a scalar. Here again, a scalar multiple of a vector is a vector. But what about this? Well, remember the dot product always means, well, the dot always means rather dot product, not multiplication. So it can't mean 3 times u. This is nonsense because this is a scalar, this is a vector. Okay, so notation matters. We have to remember to write these arrows over these vectors, and then we need to make sure that the dot from now on in when we're talking about vectors is the dot product and not use it for multiplying real numbers together anymore. If you're going to do a scalar multiplication, you just do 3 and write it right next to the vector u, or use parentheses if you're multiplying two scalars together. Okay, so what we want to do now is to get, in the next video, we're going to look at the dot product, and we want to get a component form of it so that we can extend the definition of the Euclidean inner product to 4 space and higher. This is good for 2 or 3 space. We can think about that angle theta, but we want to extend this so that we can find the dot product for vectors in 4 space or higher, and we'll do that in the next video.